created by MindSticks Foundation Trust.
Hello, students, and welcome to today's Explainer. Here is what we are going to cover today. First up, the core theorem. Then, we will look at Pythagorean triplets. After that, special angle properties, followed by proving with similar triangles. And finally, we will wrap up with the geometric mean. Let's get right into it. Section 1, the core theorem, the foundation of right-angled triangles. Before we jump into the hard math, let's just recall what we already know. Take a look at triangle PQR here. You see that little square symbol right there at vertex Q? That is our universal sign for a perfect 90-degree right angle. And directly across from it, that is the longest side of our triangle, the hypotenuse, which is side PR. Getting this visual layout locked in our minds is really the very first step to mastering this geometry. Now, the absolute heart of this is the Pythagoras theorem itself. Listen closely to this definition. In a right-angled triangle, the square of the hypotenuse is exactly equal to the sum of the squares of the remaining two sides. So what does that mean for our triangle PQR? Mathematically, it means PR squared equals PQ squared plus QR squared. Let me say that just one more time so it really sticks. PR squared equals PQ squared plus QR squared. This, my dear students, is the golden rule for all right-angled triangles. All right, moving on to section 2, Pythagorean triplets, identifying the pattern. You can think of a Pythagorean triplet as a sort of mathematical fingerprint for a perfect right-angled triangle. If you're handed 3 numbers and asked, hey, do these form a right triangle? You can use a very simple 4-step procedure. Step 1, just identify the largest number. That is your candidate for the hypotenuse. Step 2, square that largest number. Step 3, find the sum of the squares of the other 2 smaller numbers. And step 4, check if your totals match. If they are exactly equal, then congratulations, you've just verified a Pythagorean triplet. Let's actually test this out with the natural numbers 11, 60, and 61. Following our steps, 61 is clearly our largest number. If we square 61, we get 3,721. Now let's look at the other 2 sides. 11 squared is 121, and 60 squared is 3,600. So when we add 121 and 3,600 together, what do we get? Exactly 3,721. Because the square of our largest number is perfectly equal to the sum of the squares of the other 2, we can confidently say yes, 11, 60, and 61 is a verified Pythagorean triplet. But here's a really cool trick. You don't have to just memorize these numbers or try to blindly guess them. You can actually generate your very own triplets using a specific formula. Take any 2 natural numbers, let's call them A and B, and just make sure A is greater than B. Your 3 terms for the triplet will be A squared plus B squared, A squared minus B squared, and 2 times A times B. Let's do a quick example together. Let's make A equal 5 and B equal 3. Term 1 is 5 squared plus 3 squared, which is 25 plus 9, giving us 34. Term 2 is 25 minus 9, which is 16, and term 3 is 2 times 5 times 3, which equals 30. Look at that. Just through some simple algebra, we've generated a brand new triplet, 34, 16, and 30. It's an incredibly powerful tool. Section 3, special angle properties, the mental shortcuts. Now, in mathematics, we absolutely love mental shortcuts, especially when it saves us precious time during exams. Take a look at triangle LMN. This is what we call a 30, 60, 90-degree triangle. There is a beautiful, strict pattern here. The side opposite the 30-degree angle, side MN, will always be exactly 1/2 the length of the hypotenuse, LN. Furthermore, the side opposite the 60-degree angle, side LM, will always be √3/2 times the length of that same hypotenuse. The brilliant thing about this is, if you know the hypotenuse, you instantly know the exact lengths of the other 2 sides without doing any complex algebra at all. Similarly, let's look at triangle XYZ. This is our 45, 45, 90-degree triangle, or an isosceles right-angled triangle. Because those 2 acute angles are equal at 45 degrees, the 2 perpendicular sides, XY and XZ, absolutely have to be equal in length. And what is that length? It is simply 1 over the square root of 2 times the length of the hypotenuse. Again, another perfect, highly reliable shortcut for your geometric problem solving. So what is the big takeaway to permanently memorize here? It's the distinct difference in these fractional multipliers. For the 30, 60, 90 triangle, you need to remember the fractions 1/2 and √3/2. For the 45, 45, 90 triangle, simply remember 1 over root 2. Keep these multipliers crystal clear in your mind. Trust me, you will be solving complex problems much faster and with so much more confidence.
Section 4. Proving with similar triangles. The deep why.
All right, we have seen the what and the how. Now let's dive into the deep why by looking at the proof. Take a look at the large right-angled triangle ABC. Imagine we deliberately draw an altitude. That's a straight perpendicular line segment starting right from the 90-degree angle at vertex B, straight down to the hypotenuse AC. We will call this line segment BD. The geometric theorem tells us that drawing this single altitude creates two smaller right-angled triangles, triangle ADB and triangle BDC. The truly amazing part is that both of these smaller triangles are mathematically similar to the original large triangle, and because of that, they are similar to each other. Let's systematically break down the logic of this into 4 easy steps. Step 1. Identify common angles. The small triangle ADB and the large triangle ABC both share the exact same angle A. Step 2. Note the 90-degree angles. Triangle ADB has a 90-degree angle at vertex D, while the large triangle ABC has its 90-degree angle at vertex B. Step 3. Because two angles perfectly match, we can confidently apply the AA, or angle-angle similarity test. This seamlessly proves that triangle ADB is similar to triangle ABC. By using that exact same deductive logic on the other side, triangle BDC is also proven similar to ABC. Finally, step 4, transitivity. If both small triangles are similar to the big one, they absolutely must be similar to each other. It is just a brilliant cascade of mathematical logic. Section 5. The geometric mean, the final piece. This concept builds directly on the logic of those similar triangles we just proved. Now, listen carefully to the vocabulary here. The theorem of geometric mean states, in a right-angled triangle, the perpendicular segment to the hypotenuse from the opposite vertex is the geometric mean of the segments into which the hypotenuse is divided. I know that sounds a bit wordy, but let's translate that formal textbook definition into a straightforward mathematical equation. Let's recall our altitude concept. We have an altitude QS that perfectly divides the hypotenuse into two distinct segments, PS and SR. Because the two smaller right-angled triangles formed inside are similar, their corresponding sides are perfectly in proportion. When we cross-multiply those proportions, we naturally arrive at this beautifully simple formula. QS squared equals PS multiplied by SR. In plain English, the length of the altitude squared is exactly equal to the product of the two segments of the hypotenuse. We have covered a massive amount of geometric ground today, students, from the core theorem itself to generating triplets, understanding the profound proof with similar triangles, and finally, the geometric mean. But before we finish up, I want to leave you with a provocative question to really ponder. In this lesson, we focused entirely on 90-degree right-angled triangles. But what if you change the angles? If the triangle is no longer exactly 90 degrees, does this mathematical foundation still hold? And further, how do you think mastering this one singular theorem about right angles unlocks the entirety of geometry, from constructing the magnificent buildings we live in to navigating the vast stars above us? Keep wondering about these concepts, keep practicing your calculations, and I will gladly see you in our next explainer.